Yeah.
What? Why?
14 participants.
15.
15. Whoa.
Oh.
That's my students. Good kids.
Well done. Okay. The live feed is working. Hang on, need to kill the sound down here. Fantastic. You ready?
Sure.
Wow.
Hey.
Hey.
Hi.
Morning,
Hello.
everyone.
Morning.
Tack. Okay. Wow. Lovely. Before we start, let me just ask into the audience, who's got a paper today? I think we have 3.
I am sending the link.
Great. That's Leah. Anyone else? Other than the people already said they had one? Okay, no one other than the people already said it. Okay, as every week, just share the links in the chat box so people can see the paper. If you present the paper, the ones who have a paper today are the regulars, so they know the drill, but they're going to share their screen so you can see the paper and see what they highlighted as well, which is quite nice. And we just have an open discussion. As a reminder, there is no wrong questions. Chances are, if you don't understand something, someone else didn't understand it, so just ask. And we try our best to explain it. In terms of the settings, feel free to keep your video on. It's quite nice to see people in the room. But we ask you to mute yourself unless you have a question. That is it, unless I'm forgetting something. Should we just start? We have 3 papers. Ladies first, Leah.
Okay. So I'm gonna share the screen. Can you view the screen? Yeah. Okay. This is the paper published in Nature Communication, I think on the 27th of October, so last week. And it's titled The Measure of Color in Science Communication. In particular, is focused on the color maps used to represent significant results. And in particular, the focus is on rainbow-like color maps that sometimes could be confounding in the representation of data. Let me start with, in the supplementary materials, they have a lot of examples. For example, here, you can have it's the global daily temperature represented in a color scale that is the rainbow jet color scale, and you can see that the color map is going through from the blue to the red, passing through the yellow. They say that the yellow in this scale is the brightest color. And this is confusing because there is not a uniformity in the gradient of these color maps. Instead, if you use another color map, like this is the Vic color map, you have the color starting from the blue to the red, and there is a uniform gradient. And this second color map addresses this requirement to a fair representation of data, so is perceptually uniform, perceptually ordered, color vision deficit friendly, and readable in black and white. So these are all the requirements that the authors address in this paper. because if you have a color map, let me see. For example, here you can represent the color map as the increased lightness, and this increase could be like uniform. So you can see from this histogram, or in the base law color map. In the jet color map, you can see that the luminosity increment is not uniform, but you have this behavior. And also this is the cumulative representation of the lightness, and you can see that here there is a uniform increase. Otherwise, in the rainbow color map, you have this behavior that it is not uniform, and that these properties of the color maps can cause some visual errors. And you can see that here, if the color map is uniform, you don't have these errors. Otherwise, in the rainbow representation, you have that. Also, authors say that science should arrive to most people as possible, and you have a person with color vision deficits. Indeed, the color representation, you know, that is a reflection of light from an object. It also depends on the background and how your eyes record this light. And so you have the cone cells, and you can have deficits in the different wavelengths, so small, medium, and large. And the most common deficit is that you can distinguish red and green. This is the problem of the medium M cone. Or you can distinguish the red colors, so you have a reduced sensitivity to red. This is the large cone, or to the light blue, and this is the S cone. And so a color map that is represented like this, to these people will look in this way. And there are also, more rare, but there are also people who are colorblind, and so you need to translate the color map in a grayscale. And this is possible if the color maps are uniform, but this is not if you have this rainbow representation that we have seen with a specific characteristic in the lightness. And they say that there are freely available softwares that you can use to achieve this requirement for the color maps. And also they made a classification. Here you have another example that your color maps should be ordered if you look to the color gradient and also the lightness gradient. And if you have the rainbow color map, you see the order colors do not correspond to the used color maps. Instead, if you have a constant increment of colors and as we can see a uniform gradient, you have a unique match. And also you can divide color maps according to the type. That is a continuous gradient. So when the colors, you have a smooth change from a color to another, or a discrete color map where you can distinguish each color, or a categorical color map where there is not an order. And also you have cluster color maps. So when this variation is sequential, is diverging with a central point, or multi-sequential or cyclic. And they made a proper guide for all occasions. So how your data are, and which is the best way to represent this data. And they say that this is a thing that the scientific community has to address to a fair representation of data. And another thing that they stress out is the background. So the importance of the background They also have a video. I don't know, can we see? It's like a short 1 minute video that they use to represent how background can change your perception of colors. I didn't have. Here you can have the same box, but with a different background. And this is a video in the supplementary material of the paper. And so lighting and saturation are the characteristics of a color. And here you can see how the background can change the perception of the same color. And also the shape of the object can also influence this perception. So also if you have a narrow object, this is different than a larger object. And so they represent different color maps, different colors, and the grayscale translation. Yeah, this is a really artistic representation of this, this science, but it is also discussed in the view of science in the communication to the to many people as possible, and also like in the media as this one. So yes, so this was the supplementary material that they used. And so in the closing remarks, they say that, of course, is important is fair representation of data, and the maps should be perceptually uniform. You can try to you have to use color maps that are color visual deficit friendly, and there is not a single rainbow color map that fill the requirements that they pointed out in this paper. And this is, yes, a general overview. Then you can have in the supplementary materials a lot of examples. Here you have another kind of rainbow, the molar rainbow, and you can see there is not it is not these properties, and how you can represent the same image with a good color maps, and you have it's plenty of examples here. Also, like an image that we usually have, for example, in graph representation, adjacent matrix, if you focus on these squares where there is a small white dot, you have the same color near neighbors in teams different. So later, my connection is not good. Lighter and darker, you should wrap these with same background. So these between the square. And you have also many of other examples. And here are the software that you can use or color maps that you can use that here some examples. And yes, this was the paper. You have also an image of Marie Curie translated with a rainbow color map and another color map with uniform gradients. And you can see how the details are different here than in the other color maps. So different colors, but a fair representation of the original data.
Thank you, Leah. That's a very interesting paper you got there. I love that they highlight a problem and they demonstrate it nicely and they give you a solution for it. It's a very nice trajectory. Personally, I'm a bit sad because I love the jet color. Are there any questions in the audience? Michelle, I can see you right there. Yeah.
So, one, there is actually a conversion of the jet colors that look like the jet color, but is adapted for colorblind people. So it does exist. I forgot its name, but you can find it if you look on the internet. And then,
Okay.
so I was thinking, why is there no software that will convert images from from jet, or like use like the gradient of colors that is in the paper and just convert it into something more appropriate then? I think it's feasible. I don't understand why people didn't do it.
Yes, they say that usually is like the choice of authors, and the thing is that also these rainbow color maps are the defaults for in some software as MATLAB, for example, in the plot representation. And they say that yes, it's not like a difficult thing to do, but it's something that is not like there is not a good procedure, an agreement for this representation, and so they stress out this point that also reviewer editors should address this problem.
But they could have a software that does that automatically. Do you see what I mean? Like you select your gradient of colors and yep.
I haven't tried this software, but this seems that they create a color map. There is also a link.
Sorry, no. So what I mean is like a software that will download the paper with the wrong colors and convert it into the good colors.
Yes. So at the end, that not when you create the image, like at the end, only want to represent the image.
Okay.
I don't know. Here there are like the links for create the color maps, I think, not to just translate it, but I haven't tried. I haven't tried to download this. So it seems that there are color maps that you can use.
Sounds good.
I don't know if I have answered.
But I think it might also not be possible to translate some of the colors as soon as they are in, online version.
CMKY? You mean like with the conversion between RGB to CMKY? Or, yeah.
Yeah, because I think that at some point in the process of printing the paper or making it published on like online, you probably have an issue with the illumination. So the website on which the color is represented or the figure is represented has a specific like properties or something, so that colors that might have been able to be differentiated might not be differentiatable anymore in the final figure.
Yes, of course. Like if you use the right color maps at the beginning, it is better, and is what they suggest. There is not an automatic software that translates that at the end.
Okay, I can't see any other questions at the moment. I just wrote to you all in the chat. So because there's so many today, I can't see you all on my screen. So if you have a question, just raise your hand or write in the chat that you have a question and I give the floor to you. But I can't see anyone for now, so I hand over to Patrick to present his paper.
So almost there. Right, just need to tuck you out of the way. Just a minute. So today I'm just gonna highlight a paper on low dimensionality manifolds. Basically, it's a way to represent your data. As we all know, with the explosion of data and with the complexity that we're currently working with, it might be more and more difficult to actually visualize our data and see our data in a meaningful way, because there are so many features of interest, so many aspects in our data that might be meaningful for our analysis, but that cannot be depicted in a three-dimensional space that we can see anymore. One solution to do that on high dimensional data is to reduce the dimensionality of the data using, for instance, manifold learning algorithms. So one thing that they used here was t-SNE, so t-distributed stochastic approximation. And they did it over dynamic functional networks, meaning the advantage of that is that each network we've got, each functional network can be depicted as a single point in their data set. I'm just heading right onto the methods to depict this in a better way. So if we acquire data here for different ROIs for like one subject, over different ROIs, we've got a time series for each ROI depicting the activation over time. And we can transform that to using this shifting window approaches to just represent the functional connectivities here in a vectorized way. So basically, each cell here represents the functional connectivity between ROIs. And we can use this for different time windows to get a dynamic functional network. If we're doing this for all the time windows here in our data set for one subject, we have the entirety of the data set here for this subject. And we can then use PCA, principal component analysis, to gain access to functional networks, which are depicted here. Now, using manifold algorithms or manifold learning techniques, we can now reduce this dimensionality. The dimensionality is basically the number of columns you've got here. We can reduce all of them into a 2D space by means in which networks here, so one line here is a network, one dot is a network, and networks that are closer to each other, dots that are closer to each other, are more similar across multiple of these dimensions. Okay? And if we do that for different types of data, or in their case, different functional conditions, we can depict the data using, for instance, t-SNE by reducing the data. So what they had was, in a sample of almost 50 participants, younger participants and older participants, they had two different conditions. The two-back task depicted in blue, resting state depicted in green, and a one-back task depicted in orange. And you can see here that networks, when we are looking, for instance, in this contrast here, networks that were gained from the two-back task versus the rest task in green are really somewhat differentiable. So these networks in blue somewhat cluster when depicted using this algorithm, and the green networks were more depicted on the lower part. It's more obvious when we're looking at the top 2 component of a PCA, where we can see somewhat of an like horizontal split, where these networks are more likely to, or the upper parts are more likely to come from the 2-back task, and the lower networks are more likely to come from the resting state. It becomes more dizzy when we're looking at different contrasts. So here, for instance, 1-back versus rest, it's kind of all over the place. PCA is not able to distinguish it in any meaningful way. And somewhat that's also true in 2-back to 1-back. So what we can see here is actually that it's easier for this algorithm to distinguish 2-back networks, or networks that were acquired from the 2-back condition, versus networks that were derived from resting state. What's interesting is that not only on the network level we can somewhat distinguish the different tasks, but we can also distinguish networks that come from younger adults and older adults, meaning the networks that come from younger people are now depicted in purple, and the older networks coming from older people are depicted in this reddish color. Can't really see the color, so thanks for presenting the last paper on colors. But you can see here too that in the 99 variants version of the t-SNE, meaning all components are included here, up to a 99% variance representation of the original data. When we embed this, we can see that younger networks coming from younger people are somewhat more clustered or more together than the networks that are coming from older people, which kind of makes sense because we know that when looking at functional connectivity networks, there's higher variance in older people than it is in younger people, typically. Here with the PCA top 2 components, we can also see somewhat that it's distinguishable, but not so good anymore as compared to t-SNE. And when we just look at the top 2 t-SNE components, we're also seeing at least somewhat of a split, with the younger adults on top and the older here at the bottom and the middle of the screen. Instead of just doing that visually, they also used spatial clustering over the embedded dynamic networks. So for all the figures I've shown you, they also calculated the accuracy of an algorithm that classifies the data to one of the 2 groups, being, for instance, rest or 2-back, rest or 1-back, etc., etc. So is our algorithm able to classify with the different types of depiction, with the t-SNE with 99%, the PCA with the top 2 components, or the t-SNE with the top 2 components? And we can see actually higher accuracy for 2-back versus rest. That's also what we've seen, right? 2-back versus rest was quite good, was quite easy to distinguish. The accuracy falls close to chance for 1-back versus rest, and same is true for 2-back versus 1-back. And we're looking here at the t-SNE 99% component, but it's also visual in the other 2 depictions. So we can safely say that when we have a high contrast between the tasks, meaning a 2-back task which has higher working a workload, computational workload for our brains compared to resting state, then we're quite confident in whatever depiction we're using that our classifying algorithms are also capable of distinguishing between the different tasks. Here's also like a visual representation of this, where now the colors here, or the black to white, shows the decision boundary likelihood. So yeah, which basically just makes it easier for us again to see how the algorithm would try to differentiate between the two different conditions or groups or whatever. So what I find interesting here is when we are looking at this one, basically t-SNE 99% just isn't able to give us any meaningful, spatially meaningful differentiation. It kind of looks like the boundary is close to the middle or is circling the middle of the image somewhat. So I just find it fascinating to see how those algorithms are supposed to work. Same we can do for the older versus younger depiction. Yeah. So I think these manifold learning approaches are a nice way to try and depict our data in a meaningful way, despite the increasing complexity and dimensionality of our data. And with that, I think I'm just closing here. And if you have any questions, feel free to ask me something and I'm trying to answer.
Thank you, Patrick. Are there any questions in the audience?
Mish, I see you.
Okay. Yeah, I just got two questions. The first one is the t-SNE top 2 component. Is that like the t-SNE applied to the top 2 components of the PCA, or that's like the top 2 component of the t-SNE?
Top 2 components of the t-SNE.
And then they do a 2D visualization of all the components here on the left.
Yeah.
Because that's 99% of the variance. That's just a clarification that I wanted to have. Because the 2D, the two component t-SNE really look like the PCA somehow, if we can say. And the other thing is like, so it looked like t-SNE did a pretty good job segregating like the participant between one back and rest by putting like, I think the one back on the periphery and the rest in the middle. But the way the calculation of the accuracy of prediction is made is just trying to segregate in two sides of space. And I wonder whether, whether the way they look at the accuracy of the prediction is not, what do you think?
Typically, I mean, if you have so to look at the accuracy of the prediction, you obviously have to label your data. Labeling meaning that your data either belongs to older subject, for instance, or younger subjects. So you have the truth of your data. And the accuracy is basically just calculated based on the difference between what your algorithm thinks is true and what the truth really is.
Okay, because like the drawing, I see what you mean. But it looks like one back versus rest is like better segregated than with the t-SNE than with the PCA. But when we go on the table, they say that actually it's not that good. Am I right? See?
Yeah, you're right. You're right. PCA is still better. Sometimes algorithms.
I know. I'm happy PCA is better, but I'm confused because visually t-SNE seems better. It looks better segregated. That's what I mean. And I don't understand.
So you mean this is better segregated than this, or?
I mean, like if you compare one back versus rest.
Yeah.
Look, it looks really like the orange is not mixed with the green for t-SNE, and the orange is mixed with the green with PCA. And despite this, PCA will be better to separate the two. And so I was wondering whether, because I don't know.
I must admit, this is one of those cases where I would have loved the authors to read the paper
I'm sorry.
presented first, so I can see.
I understand. Okay. Well, I don't know where to go with that. I mean, sorry. That just for you to know, like there's like all the orange points are in the middle, and they're not overlapping with the green points that are on the periphery, and that's why like I found it surprising. It's no better than PCA.
Can I ask you a random question about this? So you have two conditions. You have 2-back versus rest, 1-back versus rest, and 2-back versus 1-back. So there's always two different contrasts. Is there a limit how many contrasts you can throw at this algorithm?
Well, actually, no. So, I mean, I think they just choose it to depict the data in a most comprehensive way, because it might be just too over-convoluted to depict all the different conditions in one another. And also I think it's quite clever to just show two conditions at a time, because we somewhat have an understanding of what the difference might be between 2-back and 1-back and rest, right? So it's basically, you could like simplify it to say that it's as a function of task complexity. The 2-back task is obviously more difficult and more demanding than the 1-back task, and nothing's easier than just lying in the scanner and resting, right? So I think by showing it like that, just go back to the actual figure for that, just depicting it like that, it makes it somewhat more interpretable, I think. But given that I don't have an image of everything overloaded to one another, I can't really say.
Thank you.
Sure, you're welcome.
Are there any other questions in the audience? Yes, Alma has a question.
Yeah. Hi, nice to meet you. I'm Alma. First of all, thank you, Patrick. This was really interesting. And I'm new here, so I don't know whether my question would be too naive or not. But when at the beginning you were saying that they're converting a whole network to one point, won't this method make lose a lot of information?
Yeah, so I mean, obviously you could, like, let's compare it to different algorithms or different methods of how we could try to simplify our data. Because high dimensionality always means that in our data set, we got multiple features of interest. So let's say we've got height and the color of our eyes and sex and whatsoever. In the end, we want to show which people in our, for instance, classroom would go well next to each other, right? And we can make a simple estimation by saying, okay, all people that are the same height will go along quite well with each other. That's a good predictor. So we just neglect all other information. We just leave this out, right? What this algorithm does is that it tries not to do that, but it tries to get or include all the information it got. So each column here in the PCA dimension reduction figure, which I'm circling right now, each column here is basically one of those features and one of those dimensions. And if you can imagine that you could just group up people by their height, for instance, you would just draw a line and have all people stand on that line and depending on their heights, right? But when we leave the one-dimensional space, it's not possible to do that anymore. So the algorithm tries to account for that in multi-dimensional space, where it's not limited by the boundary of what we can imagine, basically. I don't know. So this is a somewhat simplified explanation for what this algorithm is trying to do. In other words, it tries to group things or approximate the distance in multidimensional space, depending on similarity across dimensions. I cannot tell you how this would look like in mathematical terms. And I think I would just bother people trying to do it and look stupid trying to do it. So I wouldn't, but that's basically what the algorithm does. So it still tries to integrate all the information without neglecting some of the information. And obviously it still reduces, or to make us look onto these points, we have to depict it in 2-dimension or 3-dimension, right? Because we can't see 4-dimensionally. And it might be that it still loses some of the information or simply doesn't project the information on the projection that we're showing right now. It's as if you have like a 3-dimensional object, but if you just have like a projector behind it and throw it onto the wall, you have the shape of the object, but you lose the depth information. And this is somewhat what's happening here too.
Similar to what they do in artificial intelligence, kind of?
Yeah, this is an unsupervised machine learning algorithm.
Patrick, there was a comment for you from Valerio in the chat box. I don't know, Valerio, do you want to just throw it in the discussion and we can talk about it?
Yes, maybe in that figure, one back versus rest, they looks easily separable, but the category boundary is circular. So maybe the problem is that they are not linearly separable. And maybe, I don't know.
Well, you're right. It might be true that the data itself is not linear or might not be linear. So but the algorithm doesn't claim to depict linear dimensions. You can embed it in linear space, which most likely is what they've done here. But the algorithm itself, well, it depends on the algorithm they're using. So some algorithms do not, I'm not sure if that's completely true, but I think some algorithms can still estimate without having.
It's like a neural network can decode not linearly. But I think that what I was saying is that maybe for us it looks separable, but it is not linear. So instead, when you reduce the dimensionality, you can decode linearly. So and this is sometimes they do, like I have read some papers in which they show that in hippocampus and in prefrontal cortex you can do a linear decoding of some variables because it is there is a manifold in a low dimensional manifold in the data. So I think this is
Hi, I'm so sorry.
Did we just lose you, Patrick?
Your questions just overloaded my internet. It was too hard for me, I'm sorry.
In the interest of time, if you can quickly repeat the question, we can do it. Otherwise, you can continue afterwards.
We could just chat about it, probably. But...
what?
Just repeat your question.
Again, no, it's not a question. It's like I think it looks that in the figure it looks that they are not separable. They are separable, but they are not linearly. So I think this is the odd thing. I think. No, this is just.
Yeah, or it might be that they're just not too well distinguishable, right?
Mm-hmm.
Yeah. But the algorithm itself doesn't claim to project only linear, like it's generalizable for nonlinear relationships too.
I just want to stress for people who didn't know is that Patrick doesn't see the difference between orange and green, and that's why like maybe the misunderstanding is coming from. No offense.
I do see the difference. I just
Oh,
see
sorry.
it differently.
Yeah. Well, sorry. I mean, like you don't see this like you don't see it distinctly. The contrast. Thank you.
Some of the contrasts. Anyway, let's not go there. But thanks for your question. Let's chat about it some more.
Okay. There is one more paper from Michelle, and depending how long it takes, there may or may not be another one for this week. Michelle.
Do you see the paper now? Yes. All right. So I'm so happy Patrick introduced this combining of dimension into a 2D space, because this is exactly what this paper is about. And I didn't want to have to explain this part. So the title, it's a preprint, it's not been accepted yet. It's called Neuroimaging into the Multiverse. And the idea behind it is that if you run analysis a different way, particularly the preprocessing of fMRI, you might end up with different results. And these kind of papers showing that according to the processing you apply to your MRI, fMRI, or diffusion MRI lead to different results, led to very impactful papers have been published in Nature Communication, Nature Neuroscience in the past 3-4 years. But all those papers stress that we have problems, but never find any way to find a solution, rather than trying to write a consensus paper across experts in the field. The difference with this paper is they propose a solution how to, in a data-driven way, compare the different methods and decide on which one will be the optimal one. And it's called the multiverse because this is a multiverse of different way you can process your data and end up with different conclusions. Right, there we go. So they use a ground truth approach where they're trying to predict age based on a functional connectivity, particularly using graph theory, which is looking at how things are correlated together in the brain. All the code that they use is available on GitHub, so you can download it and apply it to your data set, whatever it is, if you're interested. And they applied the analysis on 298 participants with an age from 14 to 26. So by doing different kind of analysis, they did several analyses per subject, and they calculated the relationship between the different elements and produce a low dimensional space, not only of the relationship between the different parts of the brain through functional connectivity, but also of the different analysis, which will be an additional dimension to combine in this two-dimensional space. It's written here. In order to efficiently sample across a large number of analysis approaches, we need information about that general relationship, and this is achieved by building a low-dimensional space that quantifies the similarity between the approaches in terms of distance and low-dimensional space. And they did that on 50 of the participant because it is like this kind of machine learning idea that you optimize your model on a small sample of your participant, like here 50, and then you test whether it really works on the rest of your participants. So you have here trying to, come back. not on my big computer, so oops, no, yeah. All right, so we go to this page of the paper. Yeah, I can maybe do it like this. There you go. No, still not. Here we go. Right here on the right, you can see how you can do this. You use your individual functional connectivity, you do some motion correction, you have different way of doing that, and that gives you a dimension, and you threshold a different way your functional connectivity, and then that will give you different networks. And then you try to calculate the similarity between the individuals, and you put in 2-dimension really the similarity of the approach and the individual together, which gives you this nice blue to red 2-dimension embedding of the subject and the processing together. That defines the space. This is your multiverse. This is how many kind of different measurements you can have there. And then you can like label your different point there according to different measurements you want to make. And then here you have like extra comparisons at the bottom. So now what's interesting is they use this space to assess which setup of parameters and subject will be the best to predict the age, which here you have the space that they define, but the colors that you have here represent how, if I remember well, how good you can predict the age. So inside this multiverse that is reduced in 2-dimension, you can find areas where a given parameters of processing your functional connectivity together with specific measurements of graph theory are actually very accurate for predicting age. Okay, and there will be, I think, the red point versus the blue points. And by doing so, then they can apply it to their other subject and show that, confirm that it works. Then they played around with like other parameters and show, didn't really get that part, I'm gonna be honest. But I think like the approach is very promising and give really an answer and a possibility in order to find like the optimal setup of parameters you have to do your processing to answer your question. There you go, available for questions if you need.
Thank you, Misha. Are there any questions? I love the bird chirping in your background, by the way. It's very smoothing.
So,
yeah, Patrick.
So thanks. I mean, I love the title.
It's a really good title.
Yeah, really. But so basically, they try to show us that some areas within the embedded space is better for predicting things, or what's the takeaway message? Like,
so it's a combination of pre-processing. So the space, the multiverse, is defined according to different dimensions, which was, I think, really thinking outside the box. No jokes here. Where they combine parameters of the way you did the motion regression, the global signal regression, different kind of threshold, and different measurements of graph theory, which will assess the relationship between the different points in your brain. And they put all that into the embedding, and the embedding define all the range of possibilities that you have. And then once you have that, you can see which one are the one that will be the best to predict the age of the participants. So somehow you do like, you do for every point of space inside this multiverse, you do a statistical prediction and see how good you are at predicting age. And then you color that space according to the level of prediction that you have. And they give you a map of what is good and what is not good to answer your question. So most likely, if you want to predict age, you got to go into the area that is dark red, and then be like, oh, so what did we do here? Oh yeah, we did motion. We did motion regression and global signal regression this way, combined with the measurement of I don't know, betweenness centrality. Well, let's do that with 500 other subjects and predict age, because it looks like that's the best setup.
I'm just wondering if this is like, to what extent this result is generalizable to other data sets. Because as we know, the space that we embed, or the way the space is computed, the way the space is built up, is primarily based on the subject you put in, obviously, the data you put in. So you have lack of areas within your space where you have few observations for these areas, right?
I hear you. So here really, well, that's what they test by extending it to the rest of the sample, is whether this is generalizable or not. But here, if you want, like, they sacrifice 50 subjects to discover what will be the optimal setup to answer that question. Because you cannot reuse the same subject to run the analysis. That will be what we call a double dipping. But if you use new subjects, you actually into a fair game. And the idea is not to bring them into this space. The idea is just to use this space to make the good decision in terms of processing and collecting information to do your analysis, and kind of get around the problem of correction for multiple comparisons.
I would have loved if they actually use simple statistics then, like a linear regression approach.
I know.
Whether the estimates that they say are especially good for predicting actually are empirically especially good for predicting the age.
So they use I actually read the paper. I discovered the paper this morning when I woke up during breakfast. I didn't have a paper for today, so I don't have all the details. Gonna be full disclosure. But what I saw is they use Bayesian statistics, which are interesting because that allows them to also reject some parameters as not being good at all to predict the age. On the other hand, they also find the optimal parameters thanks to the Bayesian factor. What I didn't really understand is, I didn't find really the values here, but that's what I got.
Thank you very much. If there is no further questions, as far as I can see, that perfectly brings us to 1 hour. So thank you everyone for coming today, for bringing a paper. We hope you have an exciting week in science, and we see you next Monday. Bye.
See ya.
Thank you.
Bye.